Today we're going to talk about exponential functions and identify some key attributes. We're going to start with the definition of an exponential function. The definition of an exponential function is a function that has a variable in the exponent. An example of this would be y equals a times b raised to the x power, or y equals 2 to the x power, or another example could be y equals 3 times 2 to the x power. I personally would put this in parentheses like this. Then when you're looking for the y-intercept for this particular equation, you're looking for the y value when x equals 0, just like anytime we're looking for a y-intercept. And when x is 0, it's like saying y equals a times b raised to the 0 power. And b to the 0 power is 1. So that gives you a y-intercept of y equals that a value, whatever that value is in front of the term raised to the power, okay? And I'll show you all an example of that in just a moment. Then the base of the function, or the multiplier, they mean the same thing. That's the number, the product that causes the change. And that would be not the exponent, but b, the number below the exponent. That would be your b value, base b. Okay, when you're looking at the standard form of an exponential function, which is y equals a times b raised to the power of x, a is the y-intercept, and it can be written in the form, the ordered pair, 0a. A is otherwise known as the initial or starting amount. So if you're writing the equation from a word problem and they tell you that you start with $500, that's your A. That's your A value, okay? In standard form, y equals a times b raised to the power of x. B is the base value. B also describes how the function grows. Is it really steep? Is it a little less steep? And we'll talk about that when we're graphing, okay? We are going to do some sketching on these notes. We're not actually going to graph. We're going to do a little bit of sketching just so you can see what it should look like. Then, if you're looking for some key attributes from a graph, I'm going to give you a basic version. So we're going to sketch a graph. And this is like your y and your x-axis. An exponential function, when graphed, will look like this. It'll start really, really close to the x-axis, and it'll grow up, and it'll eventually cross the y-axis and continue on, okay? In this form, this value here, your initial value, is your a value. Where it crosses the y-axis is your a value. That's the point 0a. It's the y-intercept. I honestly don't know why we're writing that again, but we're writing it again. So anytime you graph it, wherever it crosses the y-axis, that's your y-intercept. That's your a value. Then if I'm looking at the same graph, and I'm going to sketch it over here, it may not look exactly the same. It'll be close enough. That point right there is your A value. Then your graph will cross over here at another point, which is 1 past. So this is like 0, 1. And this value here, we don't know it. It's a Y value that we don't know. That point right there is 1Y. And that's going to give you some information that you can use for your base. Because the base B can be found by using the equation Y over A. So if you know this value when X is 1, so say this value is 4. If you divide that value by your A value, your y-intercept, that'll give you your base. It'll give you your multiplier. Okay? So let's do a specific example here. If I told you that this right here crossed at 2, that would give me the pair 0, 2 as my y-intercept. Over here, if I knew that this one here crossed at 4, so this y value is 4. So I know that this y value is 4. Then to find B, I would say B equals 4 over 2. And 4 divided by 2 is 2, so my base value would be 2. So the equation, the combined equation from this here and this here would be y equals 2 times 2 raised to the x power. Because the base B is 2, the y-intercept is 2, so I write them in this form. Okay, that's just a specific example. Then if I was to give you a table, we can also identify the key features. So if I gave you the table in this form, x, y, and it has -1, 1/2, 0, 1, 1, 2, and 2, 4. And say you're looking for the y-intercept. Well, for the first table, we've already established that we're looking for the y-intercept when x is 0. So for this table, I'm looking for where x is 0, which is right here. And my y-intercept is the ordered pair 0, 1. Or you could say that your A value equals 1. That's for this table here. Okay? Now, if I give you a different table, what if it was -1, 2/5, 0, 2, 1, 10, and 2, 50. Again, I'm looking for x to be 0, which is this point here. So this time, my y-intercept is at the ordered pair 0, 2. My A value is 2. Now, using those same tables, oops, so I apologize, I put the wrong value because it needs to match this table over here. -1, 1/2, 0, 1, 1, 2, and 2, 4. We can find the B value by figuring out what's happening, okay? By figuring out what we're doing. So these are all changing by a +1, +1, +1, +1. Then to go from 1/2 to 1, what do we have to do? Well, to go from 1/2 to 1, I have to multiply by 2. Then to go from 1 to 2, again, I will multiply by 2. And then from 2 to 4, again, I will multiply by 2. My B value, my base value, is 2. And if we look at the second table, and actually I'm going to give you a different one this time. Again, this is increasing by 1. Over here, I have 3, and I'm making it a 1. To go from a positive 3 to a positive 1, I'm decreasing. So instead of multiplying, I'm now going to say I'm dividing. And I have to divide 3 by 3 to get to 1. So then you want to check and see if it's going to work for the next point. To go from 1 to 1/3. Well, 1/3 is literally 1 divided by 3. So I had to divide by 3 again. Then if I take 1/3 and I divide by 3 one more time, I'll get 1/9. And that's literally saying this, 1/3 divided by 3. If you're dividing a fraction by another fraction, and 3 can be written as a fraction, 3/1, then you're going to employ same change flip, which says the top fraction stays the same. I change the operation from division to multiplication, and then I flip the bottom fraction. Currently it is 3/1. I'll make it a 1/3. And then I simply have to multiply straight across. 1 times 1 is 1. 3 times 3 is 9. That's how they got 1/9. It's also something that you can do in your calculator. Okay? Now, given this table, I can also write my equation. So if I take this A value here and this B value here, that gives me the equation y equals 2 raised to the x power. Because technically what it should be is 1 times 2 raised to the x power. Because it's a 1 in front, I don't need to write it. I can simply write it as 2 to the x power. Okay? I don't have to write the 1 in front, just like any other time it's implied. There's always a 1 there. Then if we're looking at these graphs, and I'm talking about the domain, I notice that here it starts on the left with an arrow, which means it goes on forever towards the negatives, and then it ends on the right with an arrow, which means it goes forever towards the positives. Well, if it goes forever to the left and forever to the right, my domain is all real numbers, denoted by that fancy R in squiggly brackets, otherwise known as braces. We call them squiggly brackets in my class. You could also write it out as the words all real numbers. I personally prefer the fancy R because it saves me some time. Okay? Now looking at the range, I'm going bottom to top. Again, I notice the bottom of the graph starts with an arrow. And then if I go to the top of the graph, it ends with an arrow. So it's going forever towards the negative on the bottom, and it's going forever towards the positive on the top. So again, my range will include my arrows. But there's something I notice here. And if you ever go back and look, you'll notice that this line here with the arrow on the bottom will never actually cross the x-axis. It'll get closer and closer and closer like you think it's going to cross the x-axis, but it never does. That means that the x-axis is an asymptote. Okay, that's this word right here, asymptote. The x-axis is an asymptote, so we need to write an equation for that. Well, I know that the equation for the x-axis is y equals 0. That's the equation for the x-axis. Because it's the line where the y value is 0, it crosses the y-axis right here at 0, and is overlaid on top of the x-axis. Okay? So that value is going to determine my range value. So I'm going to go forever towards the positives, but coming down here forever towards the negatives isn't quite going to happen. It's going to get infinitesimally close to 0, but it's never actually going to equal 0. So that tells me that for my range value, my y values are greater than 0, not equal to. Don't put the equal to bar, okay? It's going to be really close to 0, but it's never actually going to equal 0. It's always going to be a number that's a little bit bigger than 0. But you can include all the positive numbers, okay? Now, on this last column, we've already determined that the equation for the asymptote will always be y equals 0. So I'm just going to draw you 2 examples of how you could determine your asymptote. If you were given a graph that looks like this, which is basically what we have for the other 2 pictures, you would write your asymptote as a dotted line on the x-axis. And I'm going to try to do it in a different color so you can see it. We'll see if it shows up. You would draw a dotted line at where y equals 0. And that simply tells me that you know there's an asymptote there and it'll never cross that. That's what an asymptote is. It's a boundary. An asymptote is a boundary that your graph will never cross. I know this graphed line here will never cross this boundary. Okay? Now, it can also be said if your graph was going the other direction. So say you had a negative function and they flipped it. They reflected it. Okay? So if they reflected your function and sent it the other way, the asymptote would still be at y equals 0. So you would still come in and draw a dotted line at y equals 0. And that dotted line, again, tells me my boundary. It tells me I can't go any lower than that point. Okay, that's it for the notes today. You do need to cut them out and glue them in your notebook. So, scissors, glue stick, and you'll put them in the next page in your notebook, which for my class, the next page in our notebook will be page 21, because the last page we did was 20. So the next page will be 21, which is this blank page here.